Thanks very much, Giovanni, for the introduction and also for organizing this session. I hope you see my slides. I decided my title was a bit ambitious, so I'm going to focus on one particular kind of hidden order, hidden magnetoelectric multipolar order, rather than 4 different types as they originally advertised, so I apologize for that. So let me start with a historical example of hidden order in magnetism for the sake of the students. I picked one that I think you'll all be familiar with. And these are data from the 1930s. And this is a plot of the susceptibility as a function of temperature for manganese oxide, which at the time was believed to be a non-magnetic material. And these data at the time must have been really curious. So at high temperature, they will have been understood. So in a non-magnetic material, the Langevin theory of paramagnetism explained that if you applied in a magnetic field, then the magnetic moments, which were disordered because of the thermal entropy, would start to line up along the field and induce a small magnetism. And so hence the positive susceptibility increasing with temperature, with as temperature is reduced. But this cusp would have at the time have been very mysterious. The cusp in the susceptibility indicates a critical temperature, some kind of phase transition. And because it's a cusp in the magnetic susceptibility, then it suggests a magnetic transition. And at the time, the only kind of magnetic order that was known was ferromagnetism, but of course manganese oxide was not ferromagnetic. We now know, of course, that manganese oxide is an antiferromagnet, and so this was a kind of hidden antiferromagnetic order. It was not directly measurable, but it manifested in some of the measured magnetic properties. And shortly after that the experiment was published, Néel proposed a phase transition to antiferromagnetic order and demonstrated theoretically that the observed susceptibility was consistent with such an antiferromagnetic order. But it was not measured directly for another 20 years when techniques of neutron diffraction and neutron scattering evolved to a state where it could really become unhidden and really measured directly as a kind of direct unhidden order. So what other kinds of magnetic order are still hidden? Where should we look for them? I'm going to persuade you that there are many kinds of hidden magnetic order and give you some hints about where it might be useful to look. And I'm going to focus specifically on composite orders on the grounds that many kind of simple orders have probably already been found, so they're not hidden anymore. And by a composite order, I mean a kind of order where the expectation value of one property is 0, say the expectation value of the magnetic moment might be 0. The expectation value of a second property is also 0, but some kind of product expectation value of the two operators will be non-zero. And let me give you an example. I'm going to show you, I'm going to, for the whole talk, refer to the example of the composite of magnetic dipole moment, dipole mu, and electric dipole moment R. So again, we're very familiar with ferromagnetic materials in which local magnetic dipole moments on the atoms are aligned and the net expectation value of the magnetic moment is non-zero. So there's nothing hidden in the order of a conventional ferromagnet. Likewise, ferroelectrics have an electric dipole per unit volume switchable by an electric field. The expectation value of the dipole operator, the electric dipole operator, is non-zero in ferroelectric, and all of the little electric dipoles on the atoms line up. And I have been interested for a long time in the class of materials called multiferroics, which are simultaneously ferromagnetic and ferroelectric. They have a non-zero expectation value of the magnetization and of the electric polarization. And there's nothing hidden in the order in a conventional multiferroic. But what I want to talk about today is a kind of hidden multiferroic order or magnetoelectric order in which there is no net magnetization, so the expectation value of the magnetic dipole is 0. There's no net electric polarization, the expectation value of the electric dipole is 0, but the product, this composite order between magnetic and electric dipole moment is non-zero. And such a non-zero product between magnetic dipole and electric dipole occurs in what are called the magnetoelectric multipoles. And let me first show you them first, and then I'll formalize them afterwards. So there, in a magnetoelectric multipole has a magnetization texture that can look like any of these kind of blobs here. So it could be kind of like a hedgehog, like a swirl, it's like a toroidal moment, or kind of like a quadrupole. And let me just hand-wavingly, if we look at this hedgehog, we can see that there's no net magnetic dipole moment, right? The little arrows are representing, say, local spins, and you can see on the right, they're pointing to the right, and on the left, they're pointing to the left. There's no net magnetic dipole in this hedgehog. There's also no net electric dipole. But if I take the product, if I say this is positive direction, I have positive spins. I have spins pointing along the positive direction in positive R and pointing along the negative direction in negative R. And so the scalar product between mu of R is non-zero in this hedgehog. And I can perform the same exercise for these other magnetoelectric multipoles and see that there's a composite order in spite of there being no net dipole, either magnetic dipole or electric dipole. Okay, so here's an outline of the talk. I'll formalize a little bit these magnetoelectric multipoles. I'll put them on a little bit more mathematically formal footing. And then I want to give you two examples of how they're interesting, or how they're interesting at least to me, and hopefully persuade you that they're interesting also. I'll discuss the first reason that they're interesting is that they have a relationship to the magnetoelectric effect, which is when I apply an electric field to a material, I induce a magnetization. That's how they get their name. It's called magnetoelectric multipoles because of this relationship. And I'll show you also that when one has a material that contains such magnetoelectric multipoles, there's always a surface magnetism. Even in an antiferromagnetic order, you cannot get rid of the surface magnetism. And then I'll very quickly show how both of these properties can be used to detect them experimentally, or at least to try to detect them experimentally. Okay, so a little bit of kind of formalism. If we think about, just I want to take you back to your introductory magnetostatics class. So you think about how a magnetic material, some general magnetization density, mu of R, interacts with the general magnetic field, which may be position dependent, h of R. And you all know that the interaction energy of this magnetization energy in the magnetic field is the dot product integrated over all space, right? That's just the Zeeman energy. And normally we're a bit lazy and we write this as the integral of the magnetization density times some uniform field, or just the magnetic dipole moment times the uniform field, where m here, the magnetic dipole moment, is the integral of the magnetization density over all space. And 99% of our magnetic phenomena and our magnetic devices, we can describe it at this level. This is totally a valid approximation. But of course, it doesn't work if there's any spatial variation in the magnetic field. And it's, in general, this approximation is just the first term in a Taylor expansion of the magnetization density in a spatially varying magnetic field. And if I continue going with higher order terms, the next one has an R and a mu of R times a derivative with respect to R, and then the next one up would have R squared times the magnetization times the second derivative, and so on. But I'm going to stop here because it's this term that I'm going to be interested in today. This is the term that provides the magnetoelectric multipoles. And so I can immediately see, for example, if my magnetic field is spatially varying, then I absolutely need to consider these terms. I can't just stop here because I won't capture the interaction of the magnetization density with my magnetic field in general. So these extra terms in the interaction energy then, you can see that this is a 9-component tensor. It's Ri times mu j, so it's electric dipole in the 3, say, Cartesian directions, and magnetic dipole in the 3 Cartesian directions. And it's the product of electric and magnetic dipole. And so it's going to, sorry for the typo here, it's going to then represent these magnetoelectric multipoles. And so this 9-component tensor is often written as the sum of its 3 irreducible parts. And when we do that, then these 3 irreducible parts, there's one scalar, which has the form of the hedgehog that we just looked at earlier. It's the dot product of R and mu of R. There's a vector, a 3-component vector, which is the toroidal moment, which is the cross product of R and mu of R. And there are 5 quadrupole terms which are R in one direction, mu in another. Here's the Z squared quadrupole in this sketch here. And these get called, I don't like this term really, it's called a magnetoelectric monopole moment. I'd rather call it a hedgehog because it's not a true magnetic monopole. It's a magnetization texture that has non-zero scalar product between R and mu and R. It's not a true monopole, but they're often called the magnetoelectric monopole, the magnetoelectric toroidal moment, and the magnetoelectric quadrupole. And they couple in turn to the divergence of the magnetic field, the curl of the magnetic field, and the field gradient. So whenever I have a kind of magnetization texture that has this kind of distribution of the local magnetic moments, then I will have a non-zero magnetoelectric monopole moment in my system, and so on. Okay, so why are these interesting? Mathematically, we can see that they're there if we don't have a uniform, they can be there if we don't have a uniform distribution of the magnetic field. I want to show you, of the magnetization density, sorry, and I want to show you two reasons where they show up in the physics and they provide interesting behaviors. So the first one is their relationship to the magnetoelectric effect. So let me review for you what the magnetoelectric effect is, or specifically what the linear magnetoelectric effect is. So the linear magnetoelectric effect refers to when I apply a magnetic field in some direction, I induce an electric polarization, which may be parallel or not to the magnetic field, or conversely, if I apply an electric field, I induce a magnetization that's linear in the electric field. And the proportionality constant between the applied field, magnetic or electric field, and the induced electric or magnetic dipole moment, magnetization, is called the magnetoelectric tensor. And you can see immediately from this simple form that the magnetoelectric tensor is only non-zero in materials that lack both space inversion and time reversal symmetries, the linear magnetoelectric tensor. And one can go even a little further than this. Oops, my slides have stopped forwarding. Let's try that. Okay, very good. And recognize that the detailed form of the tensor, for example, if it's diagonal, if I apply an electric field, is my induced property going to be parallel to the field? The detailed form of the tensor is, of course, determined by the structural and magnetic symmetry of the crystal. And it turns out that one can show by symmetry that when the magnetoelectric multipoles exist in a material, and they order ferroically. So I have to have the magnetoelectric multipoles on all of the atoms having the same sign. Then the linear magnetoelectric tensor is non-zero and vice versa. And one can even be a little more specific than that and say recognize that if the magnetization texture is entirely of hedgehog form, then the magnetoelectric tensor is isotropic and diagonal. So one can apply a magnetic field in any direction and induce a polarization of the same size, whatever the direction the magnetic field is applied. If the magnetization texture is entirely toroidal, the magnetoelectric response is antisymmetric and off diagonal. So I apply an electric field in one direction and I induce a magnetization in the perpendicular direction. And if the magnetization texture is entirely quadrupolar, the tensor is traceless. For the particular Z squared quadrupole shown here, it's diagonal and traceless. It can also be off diagonal for other quadrupoles. Sorry, slides not forwarding. Okay, so let's look at an example, and I'm choosing chromium 203 as the example. This is the crystal structure of chromium 203, and this is its magnetic structure. So the magnetic dipoles kind of point to each other in pairs. The oxygen atoms are shown in red here. And chromium 203 is a well-known magnetoelectric. This is a little chart of all popular magnetoelectric materials. It's not a particularly strong linear magnetoelectric. It's kind of in the middle, but it's extremely well established. It's important because it was the very first magnetoelectric to be recognized. It was predicted by Igor Jalashinsky, theoretically to be magnetoelectric at the end of the 1950s, and then it was measured a year later, and his predictions were shown to be correct, and he predicted it based on symmetry. you can kind of see from the crystal structure, it's uniaxial, it has uniaxial symmetry, and so its magnetoelectric tensor is also uniaxial. And alpha 1, 1, the response along the z-axis is different from the in-plane response. And in plane, the y, and xx responses are equal to each other. Okay, just look at these magnetic moments here on this pair of chromiums. You can see I have two magnetic moments pointing towards each other, and I can do a thought experiment even without doing any formal symmetry analysis. And I can rewrite these two spins that are pointing towards each other along Z as 4 spins pointing in here, plus 2 spins pointing in and 2 pointing out, right? If I add these together, I get back to this spin structure of chromium 203. And the 4 spins pointing in, if I did this in 3 dimensions, would look like the hedgehog that we've just been looking at. And the 2 in, 2 out look like a quadrupole, right? And so I would expect the magnetoelectric response of chromium 203 to have the response of a monopole, which was the isotropic diagonal response, plus the traceless response of the z-squared quadrupole. And this, of course, is exactly what's seen. The alpha ZZ is different from alpha 1, 1, which is equal to alpha 2, 2. And so I can recast my understanding of the symmetry of chromium 203 and its magnetoelectric response into, I can decompose it into the magnetoelectric multipoles, into the sum of the responses from the magnetoelectric multipoles. We can also go and calculate the magnetoelectric multipoles with our electronic structure theory methods. We just go and calculate the distribution of the electrons in our material, and then perform the integral of the product of the magnetization density times the position within these atomic spheres. And what we find for chromium 203 is that each of the chromium atoms has a non-zero magnetoelectric monopole, also a quadrupole, and these all have the same sign. It's ferromonopolar, as we'd expect. I didn't write down the numbers here because I'm not sure that they're particularly meaningful. We can also define a magnetoelectric multipole per unit volume, the same way as we define the magnetization to be the magnetic dipole per unit volume. We can define the magnetoelectric multipole per unit volume. And for the case of this monopole, it would then be called a monopolization. It's a monopole moment per unit volume by analogy with the magnetization or the electric polarization. And we can calculate that with the usual kind of Berry phase theory that we use for calculating electric polarization. And this is also non-zero, consistent with the magnetoelectric response. This was the PhD thesis work of Florian Turler in collaboration with Michael Feshner, who's a postdoc in the group. What I want to point out for you here, again, I didn't write down the actual number, are the units. The units of this monopole, or in general magnetoelectric multipole per unit volume, are Bohr magnetons per unit area. So the bulk thermodynamic magnetoelectric multipole per unit volume has the same units as magnetic moment per unit area. Okay, and that's going to be important in our finding a way to measure these multiples. Okay, I'm going to skip over that because I'm going to run out of time. Okay, so I've showed you hopefully why they're interesting because of this relationship to the magnetoelectric effect. And for me, it's always been helpful in thinking, if I want to think of how to design maybe a new magnetoelectric material, to think of, okay, which combination of atoms are going to have these magnetoelectric multipoles, and how should I arrange them then to engineer a net magnetoelectric effect. What I want to show you next is why they're interesting because of their surface magnetism. And again, remember the units of the magnetoelectric multipole per unit volume, which we could call the magnetoelectric multipolization, are magnetic magnetic dipole moment per unit area. And an outcome of this, and I'm not going to have time to prove this to you, I'm just going to state it, and hopefully I hope that from the kind of dimensional analysis you'll accept this. an outcome is that there's an intrinsic surface magnetization associated with the existence of bulk magnetoelectric multipoles in antiferromagnetic materials that are magnetoelectric. And you can't get rid of this surface magnetization, it's there, and it doesn't occur in an ordinary antiferromagnet. And it's there, it's a bulk property, it's a result of this magnetoelectric multipole per unit volume. For all of the technical details, I wrote an article for the 90th birthday special issue of JETP for Igor Jalashinsky. Sadly passed away just a couple of months ago. So here's the chromium-203 example. Chromium-203, as we just saw, has magnetoelectric monopoles plus magnetoelectric quadrupole moments. In this 9-component tensor, it has only non-zero the ZZ component. And its magnetoelectric multipolization is MZZ Bohr magnetons per square nanometer. When I make a surface on chromium-203, it has a surface magnetic dipole per unit area, which is equal to the size of the magnetoelectric multipole per unit volume. And because the monopole and the quadrupolar have the same top and down symmetry, I have a positive magnetic dipole. I have a magnetic dipole pointing out at the top and also pointing out at the bottom if I make two surfaces. And you can see that this is really analogous to the ferroelectric polarization. Here's my electric dipole per unit volume in a ferroelectric. The units of electric dipole per unit volume are charge per unit area. And when I cut a ferroelectric perpendicular to the polarization, I have a surface charge. The polarization is a vector, so it's positive on the top and negative on the bottom. So all of the technology, all of the computational tools and technology we have for describing electric polarization, we can apply then to describing magnetoelectric multipolization. All of the tools we have for understanding surface charge at the surface of ferroelectrics, we can use to understand surface magnetism at the surface of non-centrosymmetric antiferromagnets. Okay, so chromium-203. Here's a slab of chromium-203. It says periodic boundary conditions in this direction, and here's the pairs of chromiums with their spins pointing, in this case, towards each other that we just looked at. And based on the size of the magnetoelectric multipole per unit volume in chromium-203, we can predict a surface magnetization for this choice of surface, which comes out to be 12 Bohr magnetons per square nanometer. There's a subtlety which some of you, those of you who know about ferroelectric polarization, will might be thinking about already, which is that the ferroelectric polarization is multi-valued, and so is the magnetoelectric multipolization. And so if I accept that these surface spins, the structure of the chromium-203 surface has these kind of dangling spins, may not be ordered because they don't have exchange interactions with there's no neighbors above them, then my surface magnetization becomes 2.4 Bohr magnetons per square nanometer, and it's in the opposite direction. So if the surface were just this, say, these oxygens, it would have this value here. So let me finish then with what I think I'm just going to have time to show you one example of measuring these magnetoelectric multipoles through this surface property. And this is an example from one of the latest speakers in the session, Dennis Makarov and his colleagues, who used NV center magnetometry to map the surface magnetization on a multi-domain sample of chromium-203. So of course you need to have domains in order, otherwise your surface magnetic field is just exactly parallel and you can't detect it. But Dennis and his colleagues used NV magnetometry in a sample with domains to detect the fringing fields as one went from one domain to another. And here's a map of the red is domain of one magnetization and blue is the domain of another magnetization. And they had to do a lot of modeling to extract from because what they measure is the field strength at a certain height, to extract from that the surface magnetization. And the number that they get is, I'd say, really rather remarkably consistent with the value that you get from the picture of the magnetoelectric multipoles causing the surface magnetization. I see that I'm out of time, so I'm going to skip over our attempts in collaboration with Igor Jalashinsky to measure the the magnetoelectric multipole through its magnetoelectric response using muon spin resonance spectroscopy. Sorry, I can't get on my Zoom, I can't just skip over without going through them and just finish. And I'm going to finish rather than with a conclusion, because I don't really have any concrete conclusions with a list of open questions. Well, I guess I have one conclusion. I hope that I've convinced you that magnetoelectric multipoles form a kind of hidden order in magnetic non-centrosymmetric materials. I find them very useful. It's up to you whether you think they're relevant or not. I find them useful in thinking about designing new magnetoelectrics, also anti-magnetoelectrics. They have the right symmetry to provide the hidden order in the pseudogap phase of the cuprates, which maybe could be relevant. Can they be measured? I think with NV magnetometry, we have a measurement that's absolutely consistent with their existence. We've also been trying with muon spin resonance spectroscopy, and I'd be very happy to hear from, there's other experiments been done, beautiful experiments with neutrons and with X-rays. Be very happy to hear any other suggestions. Whether they'll be useful or not, I have no idea. I think it's useful perhaps in some cases to have an intrinsic surface magnetization. I think the exchange bias coupling should be different in a non-centrosymmetric antiferromagnet than in a centrosymmetric one because of this property. One could envisage some kind of monopole electronics or maybe some kind of novel storage, but these are really very much, I'm not advocating for any of these, but leaving them as possible ideas or future directions. So thanks a lot for your attention. I'd be happy to take any questions.